Welcome to the 8P Physics 1 review series. This is motion in one dimension. We're looking at equations and applications. This is part 1. The motion of an object is described by where an object is located and when it is at that position. In terms of where an object is, we like to look at our position, which we can denote as x. We may also be interested in its displacement, which is its change in position from a x final minus an x initial. And another way to write a displacement could be x minus x naught. It's the same thing as x final minus x initial. In terms of when, we look at time, which we can represent as t. And then we also could be interested in how quickly. That would be v for velocity, and then RA for acceleration. Some key information we should look for in all of these problems is time. Time is very important. It may be given, it may not be given, or we may need to solve for it. So time is a very key piece of information. Another key piece of information is accelerating. A question you should always ask yourself is, am I accelerating? Yes or no? Now all these problems are going to be dealing with constant acceleration, but again, it's a good idea to understand if you are accelerating and what that acceleration is. When we look at the basic mechanical units, we have two. We have length and we have time. And if we take length and we divide by time, we get speed. When we add direction to speed, we get a vector, which is velocity. And if we divide velocity again by time, that equals acceleration. Now, acceleration is the rate of change in velocity, that is, how quickly velocity changes. When we look at the units for length, we like to think about length in terms of meters. For time, we generally like seconds. And then that makes velocity as a meters divided by seconds. And then acceleration is meters per second divided by seconds again, so we get meters per second squared. Time, displacement, velocity, and acceleration are the fundamental variables to analyzing motion. We like to think of terms or time in terms of t. And then one way to rewrite t, sometimes we like to think of time as a change in time, or a final time minus initial time. Again, we can use the convention t minus t naught. It means the same thing. Delta x, we can unpack. That's our displacement. We can unpack it in terms of its position. That would be its position that we're interested in, whether it's a final position or just some other position. That's x. Then we like to look at an initial state. Perhaps it's initial condition or just whatever original position we're interested in. That would be x naught. For velocity, we like to think in terms of whatever velocity we're interested in. Perhaps it's a final velocity. And then also the initial or an original position, or excuse me, velocity. We can always combine those into our delta v, where delta v is v minus v naught. And then we have acceleration. So there's really just two basic equations that can solve any one-dimensional motion problem. These two equations are velocity is equal to v naught plus acceleration times time. And we also have displacement. The displacement of x, or delta x, is equal to the initial velocity, v naught, times time, plus 1/2 the acceleration times time squared. If we look at the variables in each equation, the first equation we have a velocity, we have a v naught, we have an acceleration, we have a time. And in the second equation we have a delta x, or displacement, we have a v naught, we have a time variable, and acceleration. So if we look at these two equations, we see that we have captured all the variables we're interested in to describe motion. again, the two basics, the displacement, time, and then understanding that is the where and time for the when, and then how quickly our position changes is our velocity and acceleration. So there are two conditions that can pose a challenge. The first condition is, what if I don't know time? And the second condition could be, what if I don't know acceleration? And what we can do is take the two basic formulas, and then we'll develop two new equations that can help us solve these problems. So let's take a look at the first one. What if I don't know time? Well, if I don't know time, there are some mathematical tricks I can do. That's rearrange some equations and solve for a particular variable of interest. We can take a look at the first two equations, and what I want to do is solve the first equation in terms of time. So I want to rearrange it and solve for time. And if I do that, time is equal to v minus v naught divided by acceleration. Now what I'm going to do with this is plug this into this equation here for time. And now what I've essentially done is now I have a new equation that does not include time. So if I plug that in, I get something that looks like this. And if I do a little work, and it's worth the effort, I'll come up with a new equation. So this doesn't look very useful as it's written right now, but what I can do is I'm going to distribute v naught here and then square this the contents of this parentheses here. So if I do that, I'm going to get something that looks like this. Alright. Now again, does it seem like I may have made this more complicated? But what actually is happening is that I can simplify this. Now where can I simplify this? Oops, I forgot an A right here. I can simplify this by this A will cancel. And what I can then see is that I have a 1 over A for both of these terms, and I can pull that out. And if I pull it out, and then multiply both sides by A over 1, I've essentially moved the acceleration to the left-hand side. And so I have A delta x is equal to what's left here. And so now what I can do is write this out again, but this time A is removed, and I can combine like terms now. So v times v naught cancels, and a negative v naught squared plus a 1/2 v naught is simply going to be a negative 1/2 v naught squared, and then I'm left with a positive 1/2 v squared. And one last thing I can do is now I can factor out a 1/2. If I factor out a 1/2 on this side, and then I multiply both sides by 2, I'll have an equation that looks like this, and I'm almost done. And then if I add v naught squared to both sides, I get a very useful equation. So it's well worth my effort to get this. V squared is equal to v naught squared plus 2a delta x. So this new equation here is written where I don't have to know time, and I can solve for acceleration, I can solve for displacement, my initial velocity, and a final velocity. So the second question, what if I don't know acceleration? Well, this one I can do another little trick. This one's a lot more straightforward. And if I look at the basic definition for average velocity, if I look at the arithmetic mean, that is, I take the sum and I divide by the number of the parts. If I'm only interested in a final velocity and an initial velocity, so let's take a look at the second question. What if I don't know acceleration? I could do another little mathematical trick. If I look at the arithmetic mean, that is, I look at a final velocity and an initial velocity, and I just want to average them. I take the two, add them up, and I divide by the number. In this case, there's two values, so the average would be v plus v naught divided by 2. Another basic definition is that my average velocity is also equal to my change in x divided by my time. And if I rearrange this equation in terms of x, my displacement is equal to my average velocity times time. Now what I can essentially do is take my mean, or my average velocity, and plug it into my displacement equation here. If I do that, I'll get something that looks like this. And sometimes I like to pull out this half, and if I pull out that 1/2, I'll get delta x. My displacement is equal to 1/2 v plus v naught times time. Alright, and this again is another very useful equation. This is solving for displacement. I could solve for velocity, I could solve for initial velocity and time without ever having to know acceleration. So let's take a look at the four that we've developed. The first three equations are actually found on our AP Physics 1 formula chart, which is very nice. And the fourth equation is not provided for us, but again, we can easily calculate it. And actually, if we want to put the work in, if we don't remember this equation, we don't have it memorized, we can easily use the combination of the first three to figure out how to solve a problem without equation number 4. And these problems look a little, or excuse me, these equations look a little bit different than those on your AP Physics formula chart. It's because delta x really doesn't show up. What they've done is they've unpacked delta x into x minus x naught. And so if you take delta x and substitute x minus x naught into them, you'll get equations that look just like the ones on your formula chart. So the variables in equation number 1, here we have velocity, here we have an initial velocity, we also have acceleration, and we have time. In equation 2, we have displacement, we have initial velocity, we have time, and we have acceleration. Third equation, we have velocity or final velocity, we have initial velocity, we have acceleration, and we have displacement. And then finally, in equation number 4, we have displacement, we have velocity final, velocity initial, and time. Notice in equation number 4, acceleration is not present. And then notice again in equation number 3 that time is not mentioned. Okay, so you can solve any one-dimensional motion problems using equations number 1 and 2. Number 3 is very useful and is provided for us. And number 4, our reason I put it in gray is because it's not given to us. So as we look at the problems in one-dimensional motion, there are just 4 basic problems, and each of them is looking at the 4 fundamental variables. So in the next video, part 2, we'll be looking at solving problems for velocity, solving problems for time, we'll be solving for displacement, and solving for acceleration.